Okay, welcome everybody. So this is the last week of actual lectures. Next week the roles are reversed. You'll be doing the lecturing and I'll listen in and pay attention, right? So we will have this entire week to at least get an overview of deep networks. So given that it's only a week, it's not going to be an in-depth overview. So it's going to be a very shallow overview of deep networks. Things that you will not find in this class are stuff like discussion whether we should be afraid of AI, because that's about as useful as discussing whether you should be afraid of knives, right? Knives cut, still we don't have nightmares of knives attacking us. Well, at least you shouldn't, and if you do, you should probably see a psychologist. Yeah, okay. With that out of the way, let's actually start with a brief overview of computers. And part of the reason why I'm doing this is to explain a little bit why at certain points of time you actually have certain algorithms being more popular than others, right? And so this is a ridiculously inaccurate, and I hope I at least got the orders of magnitude right, view of kind of what computers can do in 10-year periods. Fairly sure about the last part. As a matter of fact, probably by now it's a factor of 10 larger. But essentially, you can see a couple of things happening. So the first thing that you can see happening is that probably around the 80s, the amount of data being collected really started picking up. And by and large, you can now assume that we have about 3 orders of magnitude increase in storage or in dataset size every 10 years. This is actually called Kreider's law. And what I'm doing here is I'm looking at, well, not just single disks, because, yeah, okay, of course, you cannot get 10 to the 11 quite that easily yet on a disk, but also on what you get in what you would call a supercomputer, as in, maybe 1,000 machines or so. So what's happened is that both the number of machines has increased and the capacity of disks, and so it's quite safe to assume that, yes, we went up by about 3 orders of magnitude every decade. So 10 to the 11 is quite a typical click-through rate data set by now. It can push up to 10 to the 12. In 2000, well, 100 million was kind of a large data set. Think of when Netflix came out, right? And, well, yeah. Something in the order of 10,000 was large in the 90s. So this is when MNIST, for instance, was released. And initially, MNIST was a big data set. And before that, a lot of data was actually manually collected. And this is why you wouldn't go beyond 100 or 1,000. So that sample size of 100 is was pretty much the same for the beginning of the century. In terms of memory, similar thing happens, but note that we are actually only going up by about 2 orders of magnitude every decade. That has a lot to do with semiconductor process technology. So basically, with every die shrink, you can pack more bits on the same amount of silicon. And since companies want to keep the surface area of silicon kind of the same, and that has a lot to do with just, the cost. It also has to do with failure rate. About 2 orders of magnitude are what you get. In terms of CPU, things have been increasing at the same rate as memory. The one thing that has happened very recently is that with GPUs becoming really prevalent, we've seen 1 to 2 orders of magnitude improvements relative to what we had before. Now, why does this matter? Because the balance and trade-off between available main memory, data, and computation have changed quite a bit. And as you change this trade-off, different algorithms have their sweet spot. So in the 80s and very early 90s, deep networks were actually quite effective because, well, you had a rather limited amount of CPU and in memory, and so you couldn't actually store a quadratic matrix. So in order to store a kernel matrix, let's say 10,000 by 10,000, well, you need something like 100 million entries, which means that you need about 400 megabytes, right? So this explains roughly why kernel matrices and therefore kernel methods were super popular in the 90s, because you were exactly at that Goldilocks zone where the CPU was fast enough to actually deal with those matrices, data wasn't too big, and so you could actually easily process it. At some point, as data size increased, a lot of those algorithms that require quadratic storage got a little bit more expensive, which is why, for instance, now there are all those fast approximations like fast food and so on. But what also happened is that algorithms that were kind of nice in the 80s, which had a very different memory to computation trade-off, got popular again now in combination with fairly limited amounts of memory on a GPU with crazy amounts of computation on there. So for calibration, by now, if you spend about $300 to $400 on an NVIDIA GTX 970 or 980, you can get around 5 teraflops of computation. This is for single precision. Double precision is way slower, but for single precision, you're really in heaven by now. And this trend is only likely to increase. Okay. So that means you can actually afford doing a lot of really crazy expensive things in terms of computation relative to storage and tweak a not so large set of parameters a lot. And that's kind of what's required if you have a nonlinear, non-convex optimization problem and you want to sort of kind of get a decent solution. You basically just throw a lot of computation at it. And so what we're going to do is we're going to cover some aspects of that this week. So let's start with the perceptron. So we all have seen that thing before. So you basically have some data. Let's call them x's, and then you get an output, and this output is given by the inner product between w and x. And then I apply some nonlinearity, possibly. So this is exactly what we did in the past. And, well, you know, we basically use that to motivate things like linear decision boundaries. Now, the question is, of course, how can we make this nonlinear? Mind you, this is actually still what's making a lot of money for pretty much every major search engine in the world, right? So logistic regression models that are mostly built on linear or maybe linear and quadratic features are something that is still a very popular thing in many places, so you shouldn't underestimate this. So a couple of ways how you can make it nonlinear is, well, you layer things. And so if you think about it, what happens is you basically take a lot of those perceptrons, and then you're using as the output essentially a linear combination of what you got in the first layer. Right? And as a matter of fact, we have been doing that in the past because all we did is we basically picked functions k of xi and x, and we took their linear combinations. And those functions used to come from, well, for instance, the representer theorem, and we basically, so these were the kernel functions. Or if we did parsed windows, these were the, kernels from parsed windows. But basically, what happened is that the argument, xi, of this expression was a given. So to make this a little bit more clear, Okay. So what happened there was the following thing. So we basically had expressions of the form, for instance, exp of the minus 1/2, and I'm not just going to write this as, well, actually 2 sigma squared wi minus x norm squared, and then we had an entire summation of those terms. Right? So we had maybe coefficients alpha I here. So this was basically what we had for a standard kernel method, and this was our function f of x. Now let's just actually rewrite this a little bit so we can get this into the form of x of minus wi norm squared over 2 sigma squared times e to the, well, wi over sigma dot x times some other function gamma of x. Let's just keep it as this. And then here we have alpha I. Sum of I could maybe call those terms here w tilde I. And so there we go. So we basically have just managed to rewrite everything in terms of just simple inner products. Something else here that actually doesn't really matter that much. And then some coefficients. And if I had a deep network, well, I would have some nonlinearity. So I would get some coefficients w tilde I. I would have some nonlinearity here of wi dot x. And yeah, those two expressions are essentially the same. Right. So now here's a big difference. In a deep network, you optimize over both this term and that term here, whereas in a kernel method, you only optimize over the first term. Well, actually, that's not entirely true. It's not entirely true because as soon as you start actually doing things like learning the kernel, you will implicitly optimize over these terms. You may just express that in a slightly different way, but ultimately you're still optimizing over the WIs. So any of the learning the kernel papers So for instance, there's one that's upcoming at AirStats in like 2-3 weeks by Zicha Yang and Andrew Wilson and a few others, does exactly that. Okay. So in other words, what we're doing here isn't actually that crazy different from what we have been doing in the past. The only thing is how you lead this thing to its logical conclusion, right? Because basically what we did with kernels is we tried to be super smart about this function here. Rather than x, we would go and design some very, very clever kernel function, k of xi and x, and to pack all the smarts into this. Whereas for a deep network, we are not trying to be particularly smart about that function, but instead we are trying to be smart about the parameters. Right? So that's effectively the trade-off where we are now departing. Any questions about that so far? Okay. Everybody's very quiet. No questions? Everything's clear? Yes?
So before the inner product of wi with x, we were taking it at 0 because of a representative theorem?
Oh, sorry, what? So there's no 0 here, right? It's just that we didn't optimize over those parameters because of the representative theorem.
But that was the justification?
Yes,
okay.
Exactly. And so basically, effectively, the kernel that you pick is implicitly, how your first layer is supposed to behave. Or in other words, the choice of kernel determines the function class, the type of smoothness, the function properties that you want to look at, and then afterwards it's just a matter of solving a convex problem within that space. And so we end up with problems that possibly have a fairly largish number of parameters, but the problem is convex in them. Whereas if we use a deep network, we will not have a convex problem any longer. As a matter of fact, those problems tend to be rather unpleasantly non-convex. And then you need to do a lot of, things that are partially motivated, partially heuristic to actually update this. Okay. Any questions about that? Well, the obvious thing that you can do is, once we have two layers, we can have yet another layer. And the same thing that we did before just repeats itself again. So we basically use the outputs of the second layer to be the inputs of the third layer. So we take a linear combination, we have another nonlinearity, and everything's good. So this is really the basic idea of a fully connected deep network. So let me emphasize that this is what's called a fully connected. So this basically refers to the bipartite graph that you get between layers. All right, so between those two layers, every input node here connects to everyone here. And as a matter of fact, you can see that I was very lazy when I drew this, because these nodes here aren't really fully connected to everything else, but I was just being very lazy, and otherwise you would just see a black marsh here. So take it as inspiration, not as the actual proper graph. Okay. As a matter of fact, what you're seeing here would be closer to a convolutional network on a string, but we'll get to that eventually. Okay. Any questions about fully connected graphs? No, because that's really simple, right? So now it's kind of awkward to draw it this way, so often people draw it just as layers and matrices in between, and quite often they will not draw those matrices not as such, but they might actually draw it as so. But since I'm being very lazy and Keynote didn't really have a good primitive for trapezes, I just drew blocks, right? But sometimes you would see this. So here's what's really happening. You basically have different layers with possibly different dimensionalities. So maybe the input layer is 1,000 dimensions, and the next layer is maybe 100 dimensions. And so what you need is you need a matrix that is of size 1,000 by 100. And as you perform the matrix vector multiplication, you get another vector out of it. And, well, then you can apply your nonlinearity, and you keep on doing this. And the trick is that you basically go and iterate between this linear mapping and then some nonlinear function applied to this linear mapping. Okay, quick question. What would happen if we didn't have the nonlinear mapping? That's what?
It's just linear.
Yes, it would be just linear. Can somebody characterize it further?
With all the different layers just collapse into one.
Correct. And one more thing, namely, if you look at X4, for instance, which is here the one with the lowest dimensionality, you would basically have a linear mapping that would be rank constrained by the smallest dimensionality. So, as you correctly observed, it's an extremely stupid idea to drop the nonlinearity, because then you might as well just collapse all the layers into one. Or at least into, well, in this case, maybe two layers, right? Because you would basically have one to reduce the dimensionality and one to up project again. But that's exactly why you actually need a form of nonlinearity, right? Now, what you need in the end is also a loss function. And that loss function basically compares the output of the network with what you actually are observing or what you're trying to predict or estimate. And that difference is then what is being used to optimize over. Right? And a lot of the recent progress has been in relatively clever design of different objectives, of clever use of possibly more than one data set, or of more than one entity type. So you might, for instance, have images and captions. And what people have done is they have actually used images and captions as inputs and try to map them into a space where they are similar. And then you would go and generate captions from that space based on the images. And we'll get to that. And it's not that the deep network understands or it wants to learn or some other nonsense that sometimes people tell you when they want to advertise and push deep networks. It's basically just math. You set up a suitable objective function and you optimize. And whether the network wants to learn or not depends very much on whether you know how to do it and not whether it wants it. The deep network wants nothing. It's just math. Sorry for saying that, but I've seen too many interviews and blog posts about such stuff. Anyway, so this is, in its very simplest form, a deep network, and that's kind of state-of-the-art, maybe mid to late 80s. Right? And it's kind of hilarious when you look at a lot of deep networks papers. You have essentially references that are for the past 3 to 4 years, and then there's this 15-year gap, and then there are references back to the 80s. It's a very unique citation structure. Okay. Now, of course, what we need to do is we need to actually optimize things, right? Okay, so let's look at the layer representation. So what I have is, of course, yi is w times xi, and then xi plus 1, which is the input to the next layer, is just the nonlinearity applied to the y's. Different tutorials on deep networks have slightly different notation here, what they call x's or y's, or maybe introduce another variable, but that's what I'm going to try and keep consistent throughout the notes here. Okay. Now, in order to optimize things, at some point we will have to compute gradients with regard to our parameters. And this will lead us to something called backpropagation. And backpropagation is nothing magic whatsoever. It's simply, well, gradients and chain rule. Okay. So, as you can easily see, what I really care about is I want to get the gradient of the loss function with regard to changes of some parameter wi, or in an entire layer wj. Because up here I have my loss function, which takes this as an argument. Basically, it actually takes y and then y n as an argument, and I want to get the derivative of the output, of the discrepancy between output and what I should have output, as a function of some parameters. Okay. Now, who hasn't seen a chain rule before? Okay, that's good that no hand goes up, because this is stuff it's high school math, right? It literally is, at least German high school math. Almost certainly high school math in Asia. So if I have some function of a concatenation between f2 and f1, right, and I want to get its derivative with regard to x, then, well, what I do is I first apply the derivative of f2 with regard to its input, so let's say f1, or f1 of x really, and I need to evaluate this. And then I go and need to evaluate the derivative with regard to x here. Let's expand this a little bit. So let's say I have, 3 functions. Let's say f is f3 applied to f2 applied to f1. So in other words, f of x is really f3 of f2 of f1 of x. Right? That's really what this notation up here means. And so if we want to compute the derivative with regard to x of f of x, well, that's basically df3 df2 times then df2 df1, then we have df1 dx, and we're done. Okay. Now, imagine that x is a vector, and let's for the moment assume that, well, f maybe is a scalar. So then this is going, but f2 is also a vector, so then this is going to be a vector. df2 df1 is going to be a matrix, and this is going to be another, well, matrix. Pardon? Okay, well, when it's a row or column vector, yes, sorry. Okay, transpose it in your mind. Okay. Yeah. So now, if we, but yes. So, but you don't know whether I input x or x transposed, right? Okay. Yes, MATLAB and Python will scream at you. So what we get out of this is if you basically end up multiplying those three things together, and their product equals a vector. Right. Yeah, there we go. Now, why is this nice? It is nice because if I want to compute the derivative of this function f, I only need to perform local operations. So in other words, f3 only needs to know what f2 does, f2 needs only to know what f1 does, and f1 only needs to know what x does. And so I basically compute local vectors or matrices, depending on how the arguments go. And then, if I want to compute the derivative with regard to x, all I do is I parameterize through. And I just multiply. Okay, so now we know how f changes as a function of x. Now let's see what happens if we try changing f as a function of some other parameter. So let's assume that f is really f3 parameterized by w3. Okay, f2 parameterized by w2, f1 by w1. So what I really mean by that is that f of x is, let's zoom out, f3 of w3 and f2 of w2 and f1 of w1 and x. Close bracket. Right. Okay. So, and my goal is now to actually compute gradients with regard to w1, w2, or w3. Right? Because if I manage to compute its derivatives, then I can go and happily optimize over it. So let's see whether we can use some of the insights that we had from before, namely the chain rule here, to also compute the derivatives there. Okay. So let's actually try it out and see what happens. And I'm going through this in fairly excruciating detail simply because this is probably about the deepest in deep networks that there is in terms of how you optimize. And several people claim to have invented backprop, which I think is kind of true. They all invented it independently. Some of the people's names would be Hinton, Leca, I think Amari, so Shunichi Amari, and then I think possibly Rummelhart. And a few others. But really, this is Leipzig and Newton, right? This is differential calculus. So in other words, yes, they all can lay claim to it, but it's really 100 years earlier that this was invented. Okay, now let's see what happens here. So dw3 of f of x. Well, that's just dw3 of f3 of w3 and f2 of all this stuff. Okay. Well, we just have to compute it. Not much we can do. Now let's have a look at dw2. Well, this really depends on w2 only through f2. So I first have to compute d f3, d f2, and then I can go and compute d f2, d w2. Right? And this is, of course, at, really f1 of w1 and x. That's really it. Now, dw1 of f of x is, well, again, chain rule. So we have df3, df2 times df2, df1 times, and now I get df1, dw1 of x. Okay. Now, if we had full functions, this would just be one term longer, but I guess you don't need me to prove to you that it works for more than 3 terms as well, right? Now, what's really happened is, if you squint hard, you can recognize some terms. You recognize those red blocks. They're still here. And then you get something else here, which basically just So what really happens is that you end up propagating the partial derivatives between the arguments back from the top to the bottom. And again, so these are vectors or matrices. And you end up multiplying them together until you get to the point where you want to compute the gradient. And then you just go and actually compute the local gradient at that point. So the forward operation was very, very easy, right? You just successively go bottom up through the layers and you evaluate. And then you can actually locally already, as you're doing this, compute those partial derivatives. And then, in order to get all those gradients, all you do is you make your way back from the bottom to the top, from the top to the bottom, and you get those terms. Okay. So this is very nice because it actually means you can, algebraically write this out and you can design a very simple algorithm for it. And this is nice because actually advanced deep learning toolkits will often offer automatic differentiation to compute those gradients for you. This is good for 2 reasons. First of all, a computer, once the program is correct, is very unlikely to screw up. Whereas if you do it, you're probably going to mistype something and you will make a mistake. Secondly, it also has the advantage that the computer can then programmatically reason about what it's going to compute, optimize things, and decide on how to dispatch and lay out those operations over a set of resources. So for instance, if you have multiple GPUs, the algorithm may very well then actually decide to schedule different computations on different GPUs and also how communication is supposed to occur between them. We'll get into that in a lot more detail at the end of tomorrow when we look at various toolkits. But for now, just think of it as really good news because it means that you will have to do a lot less work. Any questions on backprop so far? Because if this is not clear, then you will have a heck of a lot of trouble with the rest of the class, at least for today and on Wednesday. Any questions would be good to ask now. Yes?
Could you do an example with actual functions?
With actual functions? Okay, so we're actually going to do that right away on the next slide. But let's go through them here, because the functions are actually very, very simple. Okay, so some of the functions may be as follows. For instance, one layer may be yi is w times xi. So in other words, f of x is just matrix times vector. In this case, well, dx is just wi. It's just wi. And dw, well, right, that's just x.
These are matrices?
Yeah, they can be matrices.
Okay.
Well, actually, it's more than that. It's times. So you get an outer product. Okay.
Why is a vector wi is a matrix?
So y is a vector,
W.
x is a vector, w is a matrix.
Then it's going to be a tensor.
No, if I have an outer product between a vector and a vector, I get a matrix.
It's like a tensor of diagonal or something.
No. So, okay, so let's be precise. Dx of y is okay. Well, see, this is, well, let's assume x and y are d-dimensional just to make things easy. So if y was a scalar, then taking the derivative of a scalar with a vector valued argument will give me a vector. So therefore, this will give me a matrix. Right. Now this is, well, okay, so here's why we're getting this specific term. So dw of y, what really happens is that each row of y is, given by, is affected by a different row in w. Because what we really have is that y is w1 in a product with x up to wd in a product with x. Right? So what I really get is that dy1, dw1, well, that's just x, and I'll get x, 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 up to, yd. So this is what I wrote here as such, and yes, okay, you're right, it technically should be a tensor, and most of its dimensions will be empty. So this is so much easier to write it this way, because you would have to collapse out things anyway.
Well, that should be one transpose x.
Yes. Again, depending on how you want to have it, yes. Get your transposes in order in your MATLAB code or in a Python or whatever code. The good thing is it will not actually run if you get the dimensionalities wrong. Yes.
And here the subset I is the layer, not the observation.
Okay, so actually, here is the layer, but then there I used the dimensionality because I didn't want to inflict double indices on you. So, okay, ignore this thing here. This is just a single layer. Right. Yeah, yes, but I did not know when I started writing that I would need to go into that much detail, and I'm lazy for not using double indices, and I think it's kind of hard to read in the back anyway. Yeah. That said, you can always zoom into the YouTube video. Any other questions about derivatives of matrices and vectors with regard to each other? Okay. Now, the next thing is you would have a nonlinearity, and well, we'll get to that later on, but I might as well do it here. So one of the typical nonlinearities that people have used is the tanh. It's this function here. And this was a fairly popular nonlinearity for a very long time. And what people realized very quickly is that it's probably not a good idea to have your network here in the saturation regime, because there the gradients vanish and you're not going to make much progress. So for instance, if you look at sets of slides like by Léon Boutou or Yann Lequin, or also by Patrice Simard, this is basically the French team from AT&T from the early 90s. The argument was basically you do not actually want to be up here in this regime. You want to be avoid saturation. And this is basically by just, clipping your arguments to the right scale. Now, this is kind of neat, but there's actually a more principled solution to it. And that's simply to use a very different nonlinearity. And this one is called ReLU. Don't worry, there's a reference on the slides, and it basically goes like so. So there's the identity here and 0 there. In other words, it's max of 0 and x. And so computing derivatives with regard to that is kind of really easy, right? Because it's either 0 or the actual value. It also leads to a bit more sparsity in the subsequent layers. And yeah, so you can do that. By the way, one thing that I completely skipped over here is the use of biases. So pretty much at every layer, you would assume that you would also have biases. In other words, we wouldn't only have something like y equals w dot x, but you would also have this plus some bias b. Okay, there was a question in the back.
So is your nonlinearity takes a scalar and returns a scalar?
Correct. So you apply this, if I have a vector, I apply it to each coordinate individually. Right. So this is the MATLAB pointwise evaluation logic. Right. Now, the latest progress in this, and this is like big progress, so this was a big progress over this, is to use that and to basically have some coefficient alpha that adjusts this. And if you want to know how this is called, it's called PRELU. It's basically somewhat tilted rectified linear units, and under certain circumstances you can actually get better outcomes with that. We may have a bit of time to get into the argument why this may be the case, but basically having a separate parameter that adjusts the slope can sometimes help. Part of the reason is that a lot more that that you don't lose out on all the information that was in the negative branch. You still get a little bit of it through. But that's really about it. Yes?
So you said you want to avoid the saturation gradient. Then why would you have saturation at all in the first place?
Well, because with this function, you do have saturation. And so the way how to fix it is either to change the inputs or to change the function. Changing the inputs was what was used for a very long time. Changing the function then solved this problem in a rather more principled manner. You can combine those two. You can use some intermediate versions. And I'm fairly sure there are data sets where this will work better. And then you can write a paper about it.
There's another question.
Yes?
You said change the input, but the input first passes through the weight matrix.
Correct.
Which can be scaled.
Yes, so I can scale the weight matrix in such a way as to make sure that the inputs to the next layer are small enough. I can constrain that weight matrix. Yes.
Okay,
So I think there was a question in the back in both slots. Okay.
By using ReLU instead of the arc tangent, you're actually increasing the saturation region boosted for the negative parts.
Correct. So basically for the negative parts, you're completely skipping them. And for the rest, you have a gradient that is 1. And so if you have several of those stacked together, then the gradients just go through exactly and will not, decay to 0. So basically, you either entirely lose a gradient by being in the negative saturation, negative region, or you push it through entirely. That turns out to work better. There is some argument why this might be the case. I think the strongest argument at the moment is simply that it works. Some of the papers argue by means of analogy, and sometimes the argument is a bit peculiar. So one paper spends an entire page writing about sex. And yeah, it's kind of why. Okay.
So is there a way by which you can actually rotate your arc tangent?
Pardon?
Is there a way by which you can actually rotate that and remap your input so that you don't quite get that same?
Is there a way to rotate the tangent?
Rotate the last function and then remap your inputs.
Well, so you can adjust you can adjust those, and there is one fairly exciting paper. Not sure whether we can get through that, which basically adjusts the transform and the scale separately. And part of the reason why this is a good idea, and I can get the reference until next time, is as follows. So when you train a deep network, you're basically optimizing over the various layers, right? And so as you're optimizing over the various layers, what happens is that initially, you go and maybe initialize everything at random. Don't set all the parameters to 0 because otherwise you're just stuck. But if you initialize, let's say, at random with maybe some small Gaussian entries, you first will start updating these parameters. And once you have a little bit of meaningful signal, you propagate through here and then there and then there and there, right? So in other words, the speed at which you're learning things may very well depend on the layer. And what now happens is that, unfortunately, so at some point you're then done and all the information comes here, and now this input layer starts changing, right? And as the input layer changes, oh my God, these subsequent layers will also need to change again, right? And then once this is finally updated, the next layer needs to update itself, and so on and so on. So in other words, you're all the time introducing covariate shift between layers, because the input layer to what you're doing next is changing as well. And so so something that was already quite optimal before all of a sudden is no longer optimal, and you need to adjust that. You can actually fight that in a fairly efficient way by at least making sure that the means and the variances are essentially unchanged as I change the input layer. So what you do is you basically go and estimate what the mean and variance would be for the previous layer. I rescale things accordingly. And then in order to address this, I allow for a separate mean shift to occur. this can accelerate convergence quite a bit. It can lead to ever so slightly better results, but it is a considerable convergence accelerator. Thanks for asking that question. If you thought of that a year ago, you could have written a really cool paper. Okay. These are all good questions, by the way. So now, here is just, and we're still at the moment just doing an overview, right? So we're at slide number 9 out of, a largest number of slides. But I think it's important to go through this gently. So this is really just, backprop what you then do. So you basically go and use the derivatives that we have layer by layer. And then we propagate our gradients through from the top to the bottom. And then at the individual points where we need to compute the derivatives with regard to the weight matrices, well, we just get, those sparse tensors, or, we just write those matrices as we would. Now, there's a couple of options that I can use. So the first thing, do not use MATLAB, right? And do not use batch solvers unless you have a really good reason why you would want to use this, right? So you basically use some form of stochastic gradient descent, possibly with a convergence accelerator. So in the simplest way, what you do is you have your parameters, you compute the gradients, and you take a tiny update step in the direction of the parameters. And I mean tiny, as in, 10 to the minus 4, 10 to the minus 5 isn't a bad idea. Possibly quite a bit smaller. And most papers by now actually publish their learning rates. This has a lot to do with the fact that the optimization problem itself is non-convex. And so the choice of learning rates can actually affect the quality of the solution that you're going to obtain. And unfortunately, there is no well understood uniform mapping between those. Yeah. This is still very much a matter of, on that kind of data, that kind of learning rate scheme works, which is probably about the worst thing that you wanted to hear, but unfortunately, that's what it is. So a couple of things you can do, though, is you can use at least some second-order information to deal with a curvature. So in other words, if I have some gradients that are always really large, I probably want to take a small step size there, because otherwise I'll overshoot. And for some parts where the gradients are very tiny because the plateau is very flat, I may want to take larger steps. Think of it this way: if you're in Grand Canyon, then okay, so this is my version of Grand Canyon. Here's a canyon, and it's very grand, right? Then if I want to take a step in this direction, it's going to be very flat. Whereas if I take a step in this direction, even small changes should affect things a lot, but I would have a large gradient there. So you basically want to dampen your steps in the direction perpendicular to the valley, and you want to accelerate them in the direction aligned with the valley. Right? And this is essentially what you're going to do for, well, basically second-order methods. And I'll get to that in a bit more detail later on. The other thing that you will probably want to do, because you will have a lot of data, is to use stochastic gradient descent. So that means you only take one instance at a time, you compute its local gradient, you take a tiny update step. The problem if you do that too much is each of those gradient steps may very well be quite noisy. So you may even have, disjoint vocabularies and whatever, so this can be very messy. What you do instead is that you use a variance reducer, and that's simply you take several observations at once, you compute the gradient from a small mini batch, and you take an update step. Now, here's a couple of things that you could learn. So you could do binary classification, you could do multiclass. We already went through this before. If you remember exponential families, a distribution over k discrete events, Well, that's basically what we have here, right? This is the log partition function. It's just a linear term. You could regress, and then you can do a lot of other things. And a very popular trend right now is to take a deep network as a feature preprocessor, and then you stuff some favorite graphical model over it. And 2 years ago, for instance, some people got a best paper prize for that. It's actually a very nice paper by Kevin Murphy and co-authors. But I'm fairly sure you could probably get a couple of other papers out by just combining the obvious. Okay, probably after this lecture, not so much anymore because everybody knows it. But yeah, this was actually done at some point in ranking. This is actually called lambda rank. So Chris Burgess was the guy who came up with this. And possibly, quite possibly at some point, this was being used in Bing. You can learn preferences, so max margin type of settings. We'll get to that in a moment. You could use that to annotate sequences in a conditional random field. Yeah, that's some of the things we could learn. So this was the overview of just, very, very high-level intro to the various components of a deep network. We're now going to dive a little bit deeper into specific layers, into specific types of connections that we could see. Any questions so far? Okay, good. So, here we go. The simplest thing is already the fully connected layer. And so here we have very simple things. In the forward mapping, we have y is w times x. And then we have the nonlinearity. And then for backprop, well, we just need to take the derivatives here with regard to the nonlinearity and then w. Sometimes people write this as separate layers, right? Sometimes you can just have these two as separate layers, one being linear and one being nonlinear but on a coordinate basis. And that sometimes makes the implementation of your code a little bit easier, but it may actually slow down your code because it can be fast to evaluate those two things jointly. And then here, dw, we get exactly that expression. That really should be a tensor, and probably the transposes are not how you think they are right now. But, okay. So this is a fairly simple general purpose layer that you could actually have. We just did that before. The rectified linear unit is exactly one of the tricks that you can use to, avoid gradients to vanish. And this was this thing here. And yeah, there's a pointer to the paper that has this in it. Okay, so you'd wonder, what is this slide doing? Is the slide doing here? Well, imagine you have the problem of determining whether there's Wally on this slide. And to be honest, I didn't spend enough time to find out whether he's on there, and he may very well be cropped off on the sides. You can do that with a deep network, and it'll probably do fairly well. But what you can already realize is if you want to do this, there's no specific property that is special to, let's say, here as opposed to there, right? So, in other words, and maybe Wally is actually there, at least there's somebody with some stripes. But the point is, there is a certain amount of translation invariance to that image. So if I were to take that entire image and shift it, it's still essentially a Where's Wally image, right? And you can still use essentially the same algorithms. So what that means is that it's actually an opportunity for us to exploit that shift invariance that's inherent in the data to constrain our parameters accordingly. Now, that's exactly what Jan Leca and co-workers did in the early 90s by coming up with a convolutional network called Lenet, and that was pretty much state of the art until maybe 1 or 2 years ago in terms of the overall structure. So if you read papers from the 90s and read papers from now, you will hardly see any difference in the architectures. It's starting to change slowly, and we'll get a lot more into what is starting to change at the end of tomorrow. Basically, the use of memory is probably the key property that distinguishes what's happening now from what was going on 20 years ago. So here's what happens. You take an input, and you convolve it with some filter. Right? So, I mean, filters are something that you would use anyway as edge detectors and contrast and directions and so on. And since you don't quite know which filter you might want to use, you pick a whole bunch of them. So in this case, well, they took a 32 by 32 image, and they applied 6 filters. Well, why 6? Because they didn't have a faster CPU. By now, you would use more. So now you have 6 28 by 28 images, and that's just because they had a, well, essentially 5 by 5 filter, right? So that's why you're losing the 2 pixels on either side. Okay. And now you have basically 6 times 28 by 28. That's a little bit large. You then go and subsample. And there are better ways than just subsampling, but you basically just average over those areas, and you get maybe 14 by 14 patches. You then go and convolve them further, maybe by using only one patch at a time, maybe by using several patches. It's really entirely up to you what you want to do there. Yeah, and in the end, you get, a large number of those maps. These guys here. And so now you have fairly nice image features. And then, since you really don't know what those image features are doing, you take a couple of fully connected layers. These here. The Gaussian connection, you could say, well, a Gaussian RBF kernel would do. And you just train them. And you can see that first you have 16 by 5 by 5. So there's 16 times 25. That's 400. Right? And then we reduce that to 120 and then to 84 dimensions. And in the end, well, since it's 10 different classes, it's an output of 10. Right. So this is basically what people used for OCR in the 90s. Yes?
So the first step, the first convolution, you take a picture, you do like 6 different kernels, and you get 6 different.
So yes, so what you do is you take the original image, and in this case they use gray-valued images because their cameras weren't particularly fancy. Remember, this was the 90s when people still used CCD cameras, so charge-coupled devices rather than CMOS. And then they get, well, 6 different filters out of it. And by now you would, of course, have red, green, and blue. And what you would typically do first is you would actually do a color space transform into HSV, for instance. So use saturation and I think vibrancy, that's what it's called, but it's basically an intensity channel and 2 channels for essentially where in the color spectrum you are. And then you basically apply some filter to this, and it can be a linear combination of several layers, and it will be a convolution within a layer. Now, the obvious question that you might ask is, well, if I implement that cheaply, well, wouldn't I want to use Fourier transforms? It actually turns out that it's faster not to use Fourier transforms, but to just brute force perform local convolutions.
So the question is, the third step, the second convolution, from the 6 images to the 16 images, what is the mapping? Because it's not integral.
Okay, so as I said before, you could have, for instance, a linear combination of all of those patches going into the same thing here. Or you could have a 1-to-1 mapping, or you could have 18 of those and, 3 come out from each one of the others. This is something that you may very well want to experiment with, right? The key point is that this is a lot cheaper than actually working on 32 by 32 images, right? So which would basically need, 1024 by, in this case, 6 times 28 times 28 number of parameters, which would be quite humongous. But on the other hand, by having a simple convolution, you only need very small sets of parameters. So for instance, in order to go from here to there, you need 6 times 5 by 5. Because the convolution size is 5 by 5, so it's 6 times 25, right? That's 150 parameters, which is very, very cheap compared to what you could end up spending otherwise. This was a big deal back in the 90s when computers were quite small. But it also turns out to be a big deal in terms of model complexity because it simply is a wonderful regularizer. So if you can get rid of a lot of ambiguity in the parameters by tying them together, that's a great idea. Yes?
So you have 10 output nodes.
Correct.
And they somehow binary encode what letter?
So yes, so you would basically have the softmax that I showed before. And basically the one that has the largest value, that's the one that you pick, and you just use, essentially, you can optimize over log likelihood. So all the things that we learned before about statistics still apply, because somehow you need to tie this output to the actual observation, right? And so what you would basically have is the log of p of y given the output. And that's really what you're trying to maximize, or rather, this to minimize. Yes?
And so did this come after attempts to approach the problem straightforwardly of, mapping strokes or things like that? And it turns out that this kind of straight brute force series of convolutions works much better than...
Okay, let me show you a few pictures. So people tried a lot, and usually they don't publish the things that don't work. People definitely used all sorts of stroke transforms and graph analysis and so on, and there's an entire subfield that is by now mostly defunct, at least I hope it is, of essentially structural analysis for strokes and similar things. This still exists in the context of handwritten character recognition. So, because there you actually do have the stroke sequence. And for instance, when you're trying to identify whether a signature is your signature or a fake, one of the easiest ways to identify this is by not just capturing what you write, but the actual writing dynamics. So when you're signing on an FPOS terminal somewhere in a store, they don't just store the grayscale image that that you write, at least I hope they don't, but they will actually store how you're signing. Because a counterfeiter may not actually be privy to the information of how you're signing. He may just see a signature. Okay. Now, what actually happens is you, and sorry, this is maybe not quite so well visible here on the projector, is you actually get all those nice edge detectors out of it. So if you look at the slides later on, or basically just search for anything along convolutional layers and filters, you would see that you get, nice, so this was actually in color images, you get certain color filters, and you get all sorts of interesting patterns out of this. Now, what this really means is that at the lowest layer, the convolutions are very similar to what your visual cortex is doing as simple structure and pattern extractors. Now, the inference from that because it works in the first layer, so therefore we know how the brain works, is of course kind of not so amazing, but people still make it. But it's perfectly reasonable to assume that, low-level, feature extractors of this form are quite good for subsequent learning. And if you think about it, the alternative is that you actually think about, well, which things could I extract? Edges are probably going to be useful for, OCR, and you manually craft those things. And as a matter of fact, for probably about 10 to 15, maybe 20 years, things like, the canny feature detector or the low and broomhead type of, sift and surf feature extractors from images were kind of the gold standard for what you would do with an image before you would do anything else with it. So what we're effectively doing here is, rather than pulling our feature extractors out of our hat, we actually use machine learning to tune those feature extractors. And that tends to work a little bit better because they're actually well suited to the data as opposed to well suited to whoever came up with them. Okay, so this is basically that first step. And it's fairly straightforward. The forward step is really just, the convolution, and for backwards, you just work out the terms. It's just really a convolution. There's nothing particularly deep to it. It's just algebra. The good news is that this is usually already implemented in pretty much any self-respecting deep networks library, so you won't even have to worry about it very much anymore. Things get more interesting once you want to introduce other layers that are new. And that happens every couple of years. Yes?
So these are mainly focused on image processing. Do you have some sort of filters for this, like text processing, for example?
Okay, very good question. What would we do for text? Actually, so for text, you need a couple of things to deal with it. First of all, text is directional. So in other words, text will make a lot more sense to you if I read it in the order it was intended, rather than reading it backwards. So for instance, if I was to talk about invariance translation have images, force brute implemented usually forward, that would sound kind of weird to you, and it may not actually be terribly understandable. So text has a direction. Secondly, other than that, you can actually treat it similarly as just a sequence, and I could convolve on it. So what people have done is they've actually used convolutions between words. They would convolve this, and then they would go and convolve that. That part. Right. And then they would go and convolve these, and so on and so on. Now, of course, this begs the question, what is a good vectorial representation of words? And we'll get to that a little bit tomorrow. So, yes, doing good deep learning on text is actually a little bit non-trivial, and maybe we'll get to it tomorrow. Now, I just want to address a little bit more of the details about layers, such that at least we get the basic architectures out of the way for today. So subsampling is kind of okay, but what actually works better is what's called max pooling. So subsampling is basically just average over that region. Max pooling takes the largest value within the region. That has the advantage that you obtain a small amount of translation invariance because, for instance, if you want to detect whether a certain attribute is present in that region, you don't care anymore quite so specifically where within that region it was. So people found that this works better. Now, the other thing that you could ask is, should I go for depth versus width? Because what I can do is I can have one 5x5 convolution, or I can have two subsequent 3x3 convolutions. And both will have the same range. As a matter of fact, the 5x5 convolution has more parameters, right? It has 25 parameters, whereas the 3x3 has 2 times 3x3, so that's 18. So you actually have fewer parameters overall. As it turns out, that deep and narrow actually beats wide and shallow. So there's a nice paper by Simonian and Sisserman, and they systematically studied this. And if you look at this, this is essentially what they used for, I think ImageNet image recognition. And so you basically have, a three-dimensional convolution and 512 filters, 512. Here they had, other narrower convolutions here. So the tricky question, of course, is what on earth does a convolution of size 1 mean? It just means another nonlinearity. So you basically scale the output, you add a constant to it, and then you have another nonlinearity. So you basically, it's really just a 3-parameter transform here. But what they found is, and by doing this full comparison, is really that deep and narrow beats wide and shallow. And then in the end, okay, you do max pooling and fully connected layers of fairly reasonable size. So 4,000 by 4,000 matrices you can still deal with. Mind you, this is where most of your parameters sit. These layers are very cheap. And as a matter of fact, this is something that started worrying some people at Google a fair amount because it's very costly to do this. So they came up with something that's called inception layers. And you should probably search for that if you want. This is after the movie. And basically, here's what they did. They said, well, essentially, instead of having a 1x1 or a 3x3 or 5x5, whatever convolution or max pooling, why not take all of those things as alternatives, and then we just concatenate all the outputs, and we use them as an input to the next layer. Or you can actually then have a small network within that, right? So you have a 1x1 and 3x3, or 1x1, 5x5, and you can do various of those things. And this is now a single layer. So this entire thing is starting to resemble more and more basically just, VLSI design where you go and combine pieces, right? And then they took many of those layers and happily optimized over it. And so you get, deep networks with 20, 30 layers. And it turns out that if you do that, you need a lot fewer of those dense, fully connected layers in the end. Now, of course, this is just an example of what can only be called whole systems training. And that was something that, they basically found actually in the late 90s. So the idea is, well, you have several units that do stuff to your input. In the end, you want to have a desired output. You have some parameters, and you just propagate your gradients back. Now, these can be layers in your deep network, but they can actually be interesting things like, a segmenter for optical character recognition, and, a graph transformer network, which turns, one parse into another parse, and an OCR module that turns image patches into, candidates for what that content might be. And that's actually what concludes it for today. You might wonder, why did they come up with this idea? And that's actually quite simple. What happened is, and I had the privilege of being in that lab at the time, they were building an OCR system. And so they had one engineer taking care of, let's say, this part here of the segmenter, the next one of, OCR, the next one of interpreting it, and then, parsing the output and turning it into English, right? And each one of those engineers worked on its part, right? There was an engineer here, there was another engineer here, and so on. Well, these people actually had names who I know, but I'm not sure they want to be known for it. But basically, most of them are authors on that paper. They put this all together, and it didn't really work. And so I think Leon Boutou was the guy who had the key idea to say, well, let's actually jointly optimize over the entire system as opposed to optimize each component separately. And that turned a system that was working okay but not great into something that just beat all the records. And that system at some point had at least 1/3 market share for optical check reading. So it was quite an impressive feat of engineering. This is a great paper worth reading, except that it's not well written. Yeah. So what we're going to do on Wednesday is we'll look at things like objectives, what you can actually happily optimize over. We'll look at things like memory. We'll look at optimization algorithms and a little bit at toolkits. And, well, so I hope you get at least some idea of how to deal with deep networks. Okay. Would you mind stopping the camera?